We are given here three equations in two unknowns, but we are not after the specific value for x or for y, but you want to find the value of x to the fifth plus y to the fifth. Let's begin by recalling that the square of a binomial is expanded as the square of the first term plus twice the product of the first and the second terms plus the square of the second term. Since we have here x squared plus y squared, let's represent this as x squared plus y squared. So let's subtract 2xy from both sides, and we arrive at this. This is our representation for x squared plus y squared, which is equal to 2. We are going to go back to this later on. Now let's represent the square of the binomial x squared plus y squared in order to get the x to the fourth plus y to the fourth term. And following the square of a binomial formula, we arrive at this expression at the left. And solving for x to the fourth plus y to the fourth, we have this expression, which we arrive at by copying the right side minus this middle term. There's no problem when the exponents are even. Now, since we want x to the fifth plus y to the fifth, let's look for an identity so that we can represent x to the fifth plus y to the fifth. But let's begin first with x to the third plus y to the third. Let's recall that if we multiply the quantity x plus y times the quantity x squared plus y squared, the result is this expression at the right. And the explanation for that is, if we distribute x to this binomial and distribute y to the binomial, the result would be x cubed plus x squared y plus xy squared plus y cubed, which is the expression at the right side. By symmetric property, we can interchange the left and the right side, and expressing this as x cubed plus y cubed, we subtract xy squared and x squared y from the left and from the right side of the equation to arrive at this equation. This is our expression for x to the third plus y to the third. Then let's express x to the fifth plus y to the fifth using the same process. If we multiply the quantity x squared plus y squared times the quantity x cubed plus y cubed, this is the result. And by symmetric property, we can interchange the left and the right side. And expressing this as x to the fifth plus y to the fifth, we now arrive at this expression. So we now have these different expressions for x squared plus y squared, x cubed plus y cubed, x to the fourth plus y to the fourth, and x to the fifth plus y to the fifth. Let's erase this part now, and let us just retain the equations that we need. We have this x to the fourth plus y to the fourth, x to the second plus y to the second. We want to find what is the exact value of x to the fifth plus y to the fifth. But let's begin with what we already know. So using now this formula for x squared plus y squared, so x squared plus y squared is equal to 2, x plus y equals 1, copy the exponent and copy minus 2xy, and solving for xy, we arrive at xy equals a negative 1/2. Let's remember that result. Next, let's go to x cubed plus y cubed. In here, we can still simplify this because there is a common factor of xy, and so we arrive at this simplified form, and replacing the values for x plus y, which is 1, x squared plus y squared, which is 2, xy is equal to negative 1/2, and y plus x or x plus y is 1. And this is equal to 5/2. Let's remember this value. Next, let's go to x to the fourth plus y to the fourth. Substituting 2 for x squared plus y squared, copy the exponent, copy minus 2, then x squared y squared is just the same as the quantity xy all raised to the second, and we know that xy is equal to negative 1/2, and so this becomes x to the fourth plus y to the fourth equals 7/2. Then we are now ready to find x to the fifth plus y to the fifth. This part here can be simplified because there's a common factor of x squared y squared, and substituting the values that we have so far, we know that x squared plus y squared is equal to 2, x cubed plus y cubed is equal to 5/2, minus x squared y squared is negative 1/2 squared, x plus y is 1, and this gives us a value of 19 over 4. And therefore, the value of x to the fifth plus y to the fifth is 19 over 4. And going back to our problem, that is letter D. We are given here 5 raised to a equals 7 raised to b equals 1,225. What is the value of ab over a plus b? And here are our options. A is 1, B is 2, C is 5, 3 is 12, and E is 25. You can pause the video and see if you can solve this Math Olympiad question. Now let's solve this problem together. Let's begin with 5 raised to a equals 1,225, and later on, we are going also to equate 7 raised to b equals 1,225. Now, using properties of equality, we can raise both sides of this equation to the same exponent, 1 over a. So the left side raised to 1 over a, the right side is raised to 1 over a. By the power of power rule, this left side can be simplified by simply multiplying the exponent a and the other exponent 1 over a. And a times 1 over a is simply 1, so our left side would be 5, and we just copied the right side. Now, from the given 7 raised to b equals 1,225, we can also raise both sides of this equation to 1 over b to arrive at this form. And by power of power rule, this can be simplified by just multiplying the exponent b times the other exponent 1 over b to get 7 at the left, and we just copied the right side. Now, since we want to get the product of a times b, let's multiply these two equations. That means we multiply 5 times 7, and at the right side of the equation, we multiply this expression to that expression. Let's do that. So 5 times 7 equals 1,225 raised to 1 over a times 1,225 raised to 1 over b. Now from here, notice that 1,225 is a common base. And let's remember that when you have x raised to m times x raised to n, meaning the base are the same, to multiply this exponential number, we just copy the common base and we add their exponents. So that is what we are going to do here. We just copy the common base and we add 1 over a plus 1 over b. And that resulted to the product of 5 times 7 is 35. We copy the base, and 1 over a plus 1 over b is equal to a plus b over ab. Notice that 1,225 can be expressed as a power of 35. We can write 1,225 as 35 squared. We copy the exponent, and of course, 35 is the same as 35 raised to the first. Let's recall that when you have an exponential number raised to another exponent, using the power of power rule, we simply have to multiply this exponent m and exponent n to simplify this. That means we can just multiply these two times this exponent to simplify the right side. And since their bases are the same, then their exponents are also equal. And so we now form this equation. The exponent at the left is 1 times the product of the exponents m and n, which is 2 times the quantity a plus b over ab. Since we want to solve this in terms of ab over a plus b, and what we have here is the reciprocal, then we multiply both sides of the equality by the reciprocal of a plus b over ab. And so we now multiply the left side by ab over a plus b, and the right side by ab over a plus b. The product of these two fractions here is 1, so what we have left is ab over a plus b times 1 equals itself. That is equal to the right side 2. And notice now that this is the expression that we want, and therefore, our final answer would be ab over a plus b is equal to 2. We are given here a Math Olympiad question. If x cubed plus 4x is equal to 8, what is the value of x to the 7th plus 64x squared? Now, let's solve this problem together. Let's begin with x cubed plus 4x equals 8, and we express this equation in terms of x cubed. So we subtract 4x from both sides of the equation to arrive at this line. Our goal is to arrive at an expression that is x to the 7th plus certain terms. So we first square both sides of this equation. So x cubed raised to the 2nd is x to the 6th. And squaring this binomial, we square 8 to get 64 minus twice the product of 8 and 4x. So we have minus 64x plus the square of 4x, which is 16x squared. Let's be reminded that we want x to the 7th. So how can we get x to the 7th if we already have x to the 6th? The answer is we multiply by x, both sides of this equation. So multiplying by x, we get x to the 7th at the left, and we distribute this x to this trinomial to arrive at 64x minus 64x squared plus 16x cubed. Again, we want x to the 7th plus 64x squared. There is x to the 7th here, there is minus 64x squared here. We can add 64x squared to both sides of the equation to arrive at x to the 7th plus 64x squared, which is this part that we want, equals to this expression at the right. Notice here that there is a common factor, 16, so we can factor out 16. We copy the left side, and factoring out 16, we have 16 times the quantity, 4x plus x cubed. But what is the value of 4x plus x cubed? Going back to our original equation, we know that x cubed plus 4x equals 8. And 4x plus x cubed is the same as x cubed plus 4x by commutative property of addition. So this expression here, inside this parenthesis, is equal to 8. Copying the left side equals 16 times 8. And so x to the 7th plus 64x squared is equal to 128. And that is now our answer to this question. We are asked to solve for a, where a is an element of the set of real numbers given this equation. 2 raised to a plus 2 raised to 3a equals 10. The first thing that we are going to do is we are going to rewrite our given equation to make it look more simple. And we can accomplish that by doing substitution. So we let the value of the expression 2 raised to a be equal to certain variable x. And then based on this substitution, we can now express the second term 2 raised to 3a as the quantity 2 raised to a all raised to 3 using the inverse of the power law of exponent. Because when you have the quantity 2 raised to a all raised to the third, we can apply the power law of exponent by copying the base 2 and multiplying the exponents a and 3 to get 3a. So the first term 2 raised to a is now x. The second term, 2 raised to 3a, is now, therefore, equal to x cubed, because 2 raised to a is equal to x, and we just copy the exponent 3. With this as our substitution, we can now rewrite the original given equation as x plus x cubed equals 10, where x is equal to 2 raised to a, and x cubed is equal to 2 raised to 3a. Next, let's rewrite this equation in descending order of power and making the right side equal to 0 by subtracting 10 from both sides of the equation. And this is now our result. This is a cubic equation, and we expect to get 3 roots. And those 3 roots could be a combination of real and imaginary roots. But in this problem, we are only after the real values of a. So, there are several ways of solving this problem. One is using synthetic division in order to apply the rational root theorem, or we can use trial and error, or we can use factoring by grouping. By inspection, looking at the original equation, one can easily see that if you let a be equal to 1, then you will arrive at a correct equation because 2 raised to 1 is 2, 3 times 1 is 3, and 2 raised to 3 is 8, 2 plus 8 is equal to 10. But since this is a Math Olympiad question, we cannot just simply assign value for a and claim that that is the solution. Also, even if you know that a equals 1 can be one of those solutions, notice that we are expecting here 3 roots. We are not just sure whether those 3 roots are all real numbers or a combination of real and imaginary roots. So in this case, let's use factoring by grouping. And we can accomplish that by rewriting this x as sum or difference of two terms in such a way that we can come up with common factors when we perform factoring by grouping. So in this case, we are going to rewrite x as 5x minus 4x because anyway, 5x minus 4x is indeed equal to x. The choice of this is because we have a constant 10 and the 5 and 5x will give us a common factor 5 when we perform factoring by grouping. So let's rearrange this also this way. First, we split x cubed as product of x and x squared, and then we rewrite 5x minus 4x as minus 4x plus 5x. Now, 5 is common between 5x and negative 10. X is common between x times x squared and 4x. So let's factor out those common factors. But first, we need to group together the first two terms and the last two terms this way. Then, factoring out now the common factor x and the common factor 5, we arrive at this. Notice that we have here difference of two squares because 4 is also a perfect square. And we can factor this out as the product of the sum and difference of the square root of x squared and the square root of 4, which is 2. So the result is this. Copy x, factor x squared minus 4x as the product of x plus 2 times x minus 2, and copy all the rest. From here, notice that the quantity x minus 2 is common between the first term and the second term. Here we have two terms separated by the plus sign. This is the plus sign. This entire expression to the left of this plus sign is considered as one factor. This expression to the right of this plus sign is our second term. So factoring out now the quantity x minus 2, this is the result. So x minus 2 is here. When you divide the first term by x minus 2, the result is x times the quantity x plus 2. When you divide the second term by x minus 2, the result is simply 5. And we copy the right side. Now, let's simplify the second factor here. We copy x minus 2 and simplify the second factor to arrive at x squared plus 2x plus 5. And we now have these factors whose product is 0, which implies that x minus 2 could be 0, or x squared plus 2x plus 5 is also 0. In order to get a product of 0, at least one of the factors must be 0. Now, let's solve first the first case. X minus 2 equals 0. Adding 2 to both sides of this equation, we arrive at x equals 2. And since x is equal to 2 raised to a, then we now have this equation 2 raised to a equals 2. Any number is implied to have an exponent of 1. And so we can write this further as 2 raised to a equals 2 raised to 1. When you have two equal exponential numbers with the same base, then their exponents must be equal. And so we now confirm that a indeed is equal to 1. And this is one of those three roots that we are looking for. Now, where are the other two roots? That would be in this quadratic equation, x squared plus 2x plus 5 equals 0. So let's solve this quadratic equation for x. Let's use this quadratic formula, and substituting the values for a, b, and c, we arrive at this result. And simplifying, we have negative 2 plus or minus, this 2 squared is 4, negative 4 times 1 times 5 is negative 20, then all over 2. 4 minus 20 is negative 16, and so we arrive at an imaginary number here. The square root of negative 16 is equal to 4i. Copy all the rest, and simplifying, we have now this result. Negative 2 over 2 is negative 1, plus or minus is copied. 4i divided by 2 is 2i, which is clearly not a real number. And since our a here is required to be an element of the set of real numbers, then negative 1 plus or minus 2i, although these are roots of the given equation, will not be accepted as the answer to this problem because of this restriction. A must be a real number. And so for our final answer, the value of a is a equals 1, which confirms what we already thought to be the value of a. But in mathematics, we cannot simply assume the value until we show mathematically that that is really the answer, especially for Math Olympiad contest where this problem was taken from. Let's say we have this blue semicircle, and let's connect points D and E to form this yellow circular segment of the blue semicircle. Then let's fold this yellow circular segment across line DE this way. in such a way that the arc and the diameter of the blue semicircle are tangent with each other. Then let's label the points. If the length of segment AB is 4 units and the length of segment BC is 2 units, find the length of line segment DE. Now let's solve this problem together. First, let's locate the center of the blue semicircle. Let's call it as point P. Now, since the diameter of the semicircle is 4 plus 2 equals 6, it follows that the length of the radius is 1/2 of 6, which is 3. So the radius is 3 units. Then it follows that the length of segment PB must be 1 unit. Then let's construct this red circle containing this yellow circular segment of the original blue semicircle. Now, there are two things that we would like to pinpoint when we draw this red semicircle. First, if you draw this line segment P up to the center of the red circle, and if we call this point of intersection as point Q, then we can say that this lower part QP is the reflection of the upper part. And so let's call this point as P prime to indicate it's the reflection of point P. That means the length of segment QP and the length of segment QP prime are equal. And this angle DQP prime is a right angle. Second, since the red circle contains this yellow circular segment of the original semicircle, then the radii of the semicircle and of the red circle must be equal. And if the radius of the blue semicircle is 3 units, then the radius also of this red circle must also be 3 units. Then let's construct this line segment from point P prime, which is the center of the red circle, perpendicular to the diameter of the red semicircle. Since the radius of the red circle is 3 units, then the length of P prime B must be equal to 3 units as well. We now have here a right triangle. The measures of the legs are 3 and 1 unit respectively. Then we can easily compute the length of the hypotenuse P prime P using the Pythagorean theorem. So P prime is now equal to the square root of the square of 3 and the square of 1, which gives us square root of 10. Since QP and QP prime are congruent, then the measure of QP prime must be 1/2 the measure of segment P prime. So the length of QP prime must be square root of 10 over 2, and the length of QP must also be square root of 10 over 2. Then let's connect this point P to this point of intersection D. Now, since P is the center of the blue semicircle, then PD is a radius of the semicircle, and its measure must be equal to 3 units as well. So we know the length of the hypotenuse, we know the length of one of the legs. We can now compute the length of the other leg, DQ. The reason why we are solving for the length of DQ is because DQ and EQ are also congruent. The line segment P prime is the perpendicular bisector of DE. So if we can find the length of DQ, then we can just double its measure and we'll find the measure of segment DE, which is what we want to find in this problem. So let's solve now for the length of DQ using the Pythagorean theorem. So DQ is equal to the square root of the square of the hypotenuse, which is 3 squared, minus the square of the leg, square root of 10 over 2. 3 squared is equal to 9. The square of the square root of 10 is 10, and the square of 2 is 4. And simplifying, we arrive at the square root of 13 over 2. At this point, there's no need for us to rationalize this. So to find out the length of line segment DE, we just need to double square root of 13 over 2. So doubling square root of 13 over 2, we arrive at square root of 26, or approximately equal to 5.10 units. And this is now our final answer. The length of the folded line DE is rounded off to 5.10 units. And this is a very neat problem. Hi everyone, here is our math problem for today. This is an item from the Ukrainian Junior Math Olympiad. Let's say we are given this simple algebra problem. A plus 1 over A equals 1 and B plus 1 over C equals 1. And we would like to find what is the value of the expression C plus 1 over A. Now let's solve this problem together. What we want to find here is the value of C plus 1 over A. Therefore, we want to find what is the expression for C and what's the expression for 1 over A, and we get the sum of those two expressions. Now, notice that the second equation has the variable C, while the first equation does not contain a variable c. So let's begin with the second equation. b plus 1 over c is equal to 1. Our goal is to isolate c in one side of the equation. In order to do that, let's first multiply both sides of the equation by c. That means each of the terms at the left side is multiplied by c, and the single term at the right side is also multiplied by c. Simplifying, the left side becomes bc plus 1, and the right side is c. Now, let's gather all the terms with variable c at the right side by subtracting bc from both sides. There's a common factor of c at the right side, so let's factor out c. And from here, we can now divide both sides of the equation by 1 minus b, and we now have our expression for c. Now, let's remember this result. We're going to use this later on. Next, we want to find the expression for 1 over a. And the first equation here has the variable a. So let's copy that equation, and then let's isolate a at the left side of the equation by subtracting 1 over b. Then we can write the right side as one fraction. Now, our goal is to get the value of 1 over a. But what we have here is simply a. So 1 over a is the reciprocal of a. So let's get the reciprocal of a, that's 1 over a. And let's get the reciprocal also at the right side, that is b over b minus 1. The numerator and the denominator switch places. So this is now our expression for 1 over a. So we are going to use now these results. So this is the expression for 1 over a, and this is the expression for c. To find now the sum of c plus 1 over a, c is equal to 1 over 1 minus b, plus 1 over a is b over b minus 1. Notice that the denominators are 1 minus b and b minus 1. If this b minus 1 is 1 minus b, then we can have a common denominator, and therefore we can easily add these two fractions. If we want to write b minus 1 as 1 minus b, we can accomplish that by changing this plus sign by minus sign, this way. Notice that if I distribute this minus sign to positive 1, this becomes negative 1, and negative of negative becomes positive b. So, in effect, these two expressions are equivalent. But the important thing is we now have a common denominator of 1 minus b. So we simply subtract 1 minus b in the numerator and copy the common denominator, 1 minus b. And this is equal to 1. Any number divided by itself is 1. So the value therefore of c plus 1 over a is equal to 1. And this is now our final answer. Find the integer solutions of ab plus c equals 2020 and a plus bc equals 2021. Now let's solve this problem together. Let's note that when we are solving systems of equations, the number of unknowns in the number of equations must be the same so that we can easily find the solution. Now in this case, notice that we have 3 unknowns and we only have 2 equations. Let's also note that the difference between 2021 and 2020 is 1. So the first thing that we're going to do is let's call the first equation as equation 1 and the second as equation 2. And let's reverse the order of the two and let's perform subtraction. So subtract the quantity a plus bc minus the quantity ab plus c. That is equal to the difference between 2021 and 2020. Then let's remove the grouping symbol. Here, there's no problem because it's preceded by plus sign. But in here, we need to distribute this negative sign. So this becomes negative ab and this becomes negative c. The right side is equal to 1. Now, there's a common factor a here and a in the third term. There's a common factor c in the second term and in the last term. So let's rearrange the order and let's factor out a and c from these two groups. Notice that we have here 1 minus b and b minus 1. The only difference is the order is reversed, but the problem is the operation is minus. But let's remember that when we have 1 minus b, that is just the same as negative of the quantity b minus 1. To check, if you distribute this, you still get this negative b, negative times negative 1, you still get positive 1. That means this 1 minus b can be replaced by this form. You now have a negative sign outside the parentheses, and you have b minus 1 inside. And therefore, you now have this b minus 1 and this negative sign outside. Notice now that we have the same factor here that we can factor out.
So the first term divided by b minus 1 is negative a. The second term divided by b minus 1 is positive c. The right side is still 1. Then we can also rearrange the order here to make the second factor be equal to c minus a. All the rest are just copied. What does this mean? We have here a product of two numbers that is equal to 1. And those two numbers are both integers. So what two integers, when multiplied, resulted to 1? There are only two possible ways. One is the first factor is 1 and the second factor is 1, or the first factor is negative 1 and the second factor is negative 1. So that means this b minus 1 could be positive 1 when c minus a is also positive 1, because their product is 1. But when b minus 1 is equal to negative 1, then c minus a must also be negative 1 so that the product is positive 1. So let's take a look at these two cases. So we have two cases here, and we are going to solve for a, b, and c in both of these cases. So let's take a look at this part here. b minus 1 equals negative 1. Then adding 1 to both sides of the equation, we have b equals 0. So we now have one value for the variable. Next, let's bring back these original equations. And let's substitute now the value of b to the variable. So if b equals 0, this becomes 0, and therefore c is equal to 2020. In the second case, if b equals 0, this becomes 0, so a is equal to 2021. So we now know what's the value of b, the value of c, and the value of a. So we have one set of solutions for this case. And these are the three results. Next, in the other case, let's take a look at this part here. b minus 1 equals positive 1. Adding 1 to both sides of the equations, that resulted to b equals 2. So again, we have the value of b now here to be equal to 2. And let's get our original equation again and substitute 2 for all instances of b in these equations. So we have a times 2 is 2a, copy the c and copy the right side. Here, a plus 2 times c. So we have here 2c, then copy all the rest. Now we can solve this equation as a system of equations through elimination. We are going to multiply the second equation by negative 2. So here is the result. This a times negative 2 becomes negative 2a. This 2c times negative 2 becomes negative 4c. This 2021 times negative 2 becomes negative 4042. Then just copy the first equation. Then solve this by elimination. 2a minus 2a is 0. 1c minus 4c is negative 3c. 2020 minus 4042, that is equal to negative 2022. Divide both sides by negative 3. We now have the value for c. So we have the value for b, we have the value for c. We need to find the value for a. So let's find the value of a. So take again our first equation here. ab plus c equals 2020. We know the value of b and c, so substitute the value for b and for c. So we now have 2a plus 674 equals 2020. Then subtract 674 from both sides and divide by 2. We found that the value of a is 673. So we know the value of a, we know the value of c, and we know the value of b. We have the three values at the left side. So let's gather them all together. And this is now the result. To check, let's bring back our original equation and let's substitute these values to the original equation. So starting from here, when a is 2021 and b equals 0 and c is 2020, we have this equation, but this part here is 0. So what's left is 2020 equals 2020, which is correct. Then take the second equation. A is 2021, b is 0, c is 2020. Again, this part here is 0. So we have 2021 equals 2021, which is correct. And at this left part, take this first equation. A is 673, b is 2, and c is 674. So multiply this to arrive at 1,346 and add these two to arrive at 2020 equals 2020, which is also correct. Then take the second equation and substitute A equals 673, B is 2, and C is 674. Then perform the arithmetic computation. We again arrive at 2021 equals 2021, which is also correct. So it's verified that in this given system of equations, there are two sets of solutions. First, we have A equals 2021 and B equals 0 and C equals 2022. Or we can take this other set of solution, A equals 673 and B equals 2 and C equals 674.
Is it possible to write the 11 whole numbers from 1985 to 1995 in some order so that the 44-digit number you get is prime? To understand this problem, let's list down those 44-digit numbers. We start from 1985 to 1986 and continue until 1995. If you count all the digits in this number, there are 44 of them. Now, as this is written, we know this is not a prime number because this number, this 44-digit number, ends with 5. And we know that when a number ends with 5, that number is divisible by 5. But since this large number is composed of 44 digits coming from 11 whole numbers, it's possible for us to, let's say, interchange 1993 and 1995, and we form again another 44-digit number. And now we do not know if this number is prime or not. This ends with digit 3, and 3 is an odd number, so it's not easy for us to tell whether this number is prime or not. So how can we know whether this number is composite or prime? In order to answer this, let's recall our divisibility test for 11. A number is divisible by 11 if the sum of the digits in the odd places and the sum of the digits in the even places have a difference that is a multiple of 11 or 0. So we want to know the sum of the numbers in the odd places, we want to know the sum of the digits in the even places, and we will get the difference of those two sums, and then we'll check whether the resulting difference is divisible by 11 or if it is 0. So let's carry that out. Let's begin by identifying the numbers in the odd places and the numbers in the even places. We color the numbers in the odd places blue and we color the numbers in the even places red. And let's get the sum of all the digits that are colored blue. So for 1985, let's add 1 plus 8 because these are the numbers in the odd places, and do the same thing for the remaining numbers. And then let's find the sum. 1 plus 8 is 9, and all these digits sum up to 9, here 10 up to here. There are 1, 2, 3, 4, 5, 6, 60 plus 45 equals 105. So the sum of all the blue digits, that means the sum of those digits that are in the odd places is 105. Then let's get the sum of all the red colored digits. And the sum of all of this is 149. Then let's get the difference of 105 and 149. So what we're getting here is the sum of all those digits in the odd places minus the sum of all those digits in the even places. And this is equal to negative 44. So clearly negative 44 is divisible by 11. And so our conclusion is that this 44-digit number formed by listing down the 11 whole numbers from 1985 to 1995 is a composite number. This is not a prime number. But what happens if we rearrange the numbers? Let's interchange 1988 and 1989. Is this number still divisible by 11? Let's check the positioning of the digits in the odd and even places. Notice that if I interchange these two numbers, 1 and 8 are still in the odd place. The same with 1 and 8 here. These 9 and 9 are still in the even place. The same with 9 and 8 here. So there is no change in the designation of the blue and the red digits. They still belong to the same color, even if we interchange the numbers. Now, let's take a different pair. Let's say 1986 and 1993. So here, 1 and 8 are in the odd place. 9 and 6 are in the even place. The same with the blue digits and the red digits here, respectively. If I interchange these two numbers, notice that this 1 and 9 are still in the odd place. We have 1, 2, 3, 4, 5. So this is in the 5th place. This is in the 7th place, which are still odd places. And the 9 and 3 are in the even place. So, what we learn from here is no matter how we rearrange the digits, their designation as in the odd position or in the even position will not change. And because of that, we can say that no matter how we rearrange these 11 numbers, the sum of the digits in the odd place would always be 105, and the sum of the digits in the even place would always be 149, and the difference would always be negative 44. And because of that, this 44-digit number would always be divisible by 11. And so going back now to the question, is it possible to write these 11 whole numbers so that the 44-digit form is prime? The answer is no. Now, let's solve this problem together. Let's analyze the question. We have here x cubed, we have here y cubed. So this is a cubic equation. Let's recall the cube of a binomial. Let's recall that if we have this cube of a binomial, the expansion of this would be, first let's recall the Pascal triangle. So the first coefficient is 1a cubed plus this 3 as the coefficient, and we take the first term a raised to the second term raised to the first, plus this 3 again, a to the first, b squared, plus b to the third. So this is the expansion. We have here a cubed followed by 3a squared b. But the problem is we have here 9x squared y. So following this cube of a binomial, if we take the cube of the binomial x plus 3y, notice that this is equal to the cube of the first term, x cubed, plus this 3 times the square of the first term, x squared, times the second term, 3y, plus 3 again, times the first term, x, times the square of the second term, 3y squared, plus the cube of the second term, 3y. This simplifies to x cubed plus 9x squared y plus 3 squared is 9 times 3 is 27 x y squared plus 3 cubed again is 27 y cubed. Notice now that this x cubed plus 9x squared y is exactly the left side of the first equation, but our problem is the second equation. How can we transform this into this one? Again, notice that if I multiply this by 27, the left side of the second equation becomes 27y cubed plus 27x y squared, and the right side becomes 54. Notice now that this part here is exactly the last two terms of the expansion of the cube of x plus 3y. You just have to apply the commutative property here. And that's the beauty of this Math Olympiad problem. So we are now ready to solve this problem. So solving now these two equations simultaneously, where the second equation now is this part, and we arrive at this by multiplying the original second equation by 27. Notice that if we add x cubed plus 9x squared y plus 27y cubed plus 27xy squared, that is this part here, and that is equal to the binomial x plus 3y raised to the third, and the right side becomes 10 plus 54, which is equal to 64. Now, since we are solving this for the set of real numbers, we can just take the cube root of both sides of this equation, and therefore we have x plus 3y is equal to 4, and solving for x is equal to 4 minus 3y. Now, we can substitute this to the first or the second equation. But we will try to avoid the first equation because this is raised to the third and it would be difficult to raise this to the third. So let's take the original second equation. So substituting this to the original second equation, we have y cubed plus, our x now is 4 minus 3y, so we're in this part, times y squared equals 2. And simplifying, we have y cubed plus 4y squared minus 3y cubed equals 2. Y cubed minus 3y cubed is negative 2y cubed. We copy the 4y squared, that is equal to positive 2. And we can solve for y cubed by dividing this by negative 2. And so we now have this part here is positive y cubed minus 2y squared. This is negative 1. When it transferred to the left, becomes positive 1 equals 0. This is a cubic equation, and we can solve for the value of y here using synthetic division. Okay, using synthetic division, let's take the coefficients first. We have 1, we have negative 2, There's no linear term here for y, so we inserted 0 and then 1. And using the rational root theorem, we know that the divisor would be a factor of this constant divided by the coefficient of 1 here. So 1 divided by 1 is 1. So we can divide this by 1. Dividing by 1, bring down 1. 1 times 1 is 1. Negative 2 plus 1 is negative 1. Negative 1 times positive 1 is negative 1. 0 plus negative 1 is negative 1. Negative 1 times positive 1 is negative 1. And 1 plus negative 1 is 0. So that means y equals 1 is a solution. Now, since this is cubic, we expect 2 more. This depressed polynomial is equivalent to y squared minus y minus 1 equals 0, which is a familiar quadratic equation. Using quadratic formula, we can show that the root of this is the golden ratio. So let me show you. So using quadratic formula, y is equal to negative b, where our b is negative 1, so that becomes positive 1, plus or minus the square root of b squared, our b is negative 1, and squaring negative 1 is positive 1, minus 4ac. So we have 4 times this 1 here, times our c is negative 1, so this becomes negative 4. So we have minus negative 4 all over 2a, where our a is 1 all over 2, which is equal to 1 plus or minus the square root of 5 over 2, which is the golden ratio. So we now have 3 roots for y. Y equals 1, y equals 1 plus square root of 5 over 2, and the third one is y equals 1 minus the square root of 5 over 2. So let's summarize our values for y, and we still need to find the values of x. So we know that y is equal to 1. We know also that y is 1 plus square root of 5 all over 2. And the third value for y is 1 minus square root of 5 over 2. We need to find the corresponding x values. And how can we find x? Notice that we have this equation for x. If y equals 1, this becomes x equals 4 minus 3 times 1. So x is equal to 4 minus 3, which is equal to 1. That is one value for x. Now, if x is 1 plus square root of 5 over 2, this equation becomes x equals 4 minus 3 times the quantity 1 plus square root of 5 all over 2. Simplifying, this is equal to x equals 4, distribute negative 3 to this binomial here. Negative 3 times 1 over 2 is negative 3 halves, minus 3 square root of 5 over 2. We distribute this monomial factor and we split 1 plus square root of 5 over 2 into 2 fractions. And this gives us x equals 4 minus 3 halves is 5 over 2 minus 3 square root of 5 over 2, which we can write as 1 fraction, 5 minus 3 square root of 5 over 2. So, when y is 1 plus square root of 5 over 2, x is 5 minus 3 square root of 5 over 2. Then when y is 1 minus square root of 5 over 2, we use again the same formula. X is equal to 4 minus 3 times 1 minus square root of 5 all over 2, which is equal to 4 minus 3 halves plus 3 square root of 5 over 2. So 2 times 4 is 8 minus 3 is 5 over 2 plus 3 square root of 5 over 2, which can be written as 1 fraction, 5 plus 3 square root of 5 over 2, which is now the remaining x value. So to summarize now our answers, we have 3 ordered pairs. If x is 1, y is 1. The other one is when x is 5 minus 3 square root of 5 over 2, y is 1 plus square root of 5 over 2. And the other solution is when x is 5 plus 3 square root of 5 all over 2, y is 1 minus square root of 5 over 2. So these are the solutions to this system of equations. Hi everyone, here's our math problem for today. Let's say we are asked to solve for the value of x given this equation. X raised to x cubed is equal to 256. You can pause the video and see if you can solve this algebra problem. the first thing that we are going to do is we are going to think of a strategy. And the strategy that we are going to use here is we are going to make both the base and the exponent equal. In here, the base is x and the exponent is x cubed. We would like to make both the base and the exponent equal. So let's recall some properties of exponents. Let's recall the power of power rule. When we have the quantity x raised to a raised to another exponent b that is equal to the base x, and then we multiplied the exponent a and the exponent b to get ab. But since multiplication is commutative, we can also interchange this a and b, and still this property works. So how can we implement the strategy? Remember, we want to make the base and the exponent equal. Since we already have here an exponent 3, then let's raise the left and the right side of this equation to exponent 3. And this is the result. Then applying this law of exponent, we can now multiply the exponent x cubed and this exponent 3 to arrive at this result. Notice now that x cubed times 3 is equal to 3x cubed, and then we just copy 256 cubed. Now, applying the converse of this law of exponent, if we have x raised to a times b, that is equal to the quantity x raised to a all raised to b. So here, you can think of 3 as our exponent a here, and you can think of x cubed as our b here. And that can be written in the form, the quantity x raised to a, that is now our x raised to the third, all raised to b, and our b here is this x cubed. The right side is just copied. So notice now that at the left side, we have x cubed as the base and x cubed as the exponent. And that is precisely what we mean by this statement here. Make both the base and the exponent equal. Now, we let a be equal to x cubed. And so if x cubed is equal to a, then we can now write this left side of the equation as a raised to a equals the right side 256 cubed. Then let's look at the prime factorization of 256. Its prime factorization is 2 raised to 8. So we can now replace this 256 by 2 raised to 8. Then remember again that by this law of exponent, because multiplication is commutative, you can interchange a and b. That means you can also interchange this exponent 8 and 3 to have this form. Notice that 8 and 3 are interchanged. Why did we do that? Notice now that 2 raised to the third is equal to 8, and the exponent outside here is 8. In other words, we now have the base 2 to the third equal to the exponent 8, because 2 to the third is equal to 8. And so, we now say that a raised to a is equal to 8 raised to 8, which means that the value of a is equal to 8. But remember that we let a be equal to x cubed. So, if a equals 8, then 8 is equal to x cubed. And from here, if we take the cube root of both sides, we now have x equals 2. And that is now the value of x, given this equation, x raised to x cubed equals 256. So let's check if this is correct. Substituting now x equals 2 to the original equation, we have 2 raised to 2 cubed equals 256. When we evaluate this tower of exponents, we evaluate first the top 2 to the third, which is equal to 8, and then we copy the base, and then we evaluate 2 to the 8, and that is indeed equal to 256. So x equals 2 is our final answer. And this problem is now solved. Hi everyone, here's our math problem for today. Find the positive integer solutions of 4 raised to a minus 36 raised to b equals 28. This is a Diophantine equation, and we are interested in finding all the pairs of positive integer solutions if they exist. You can pause the video and see if you can solve this problem. Now let's solve this problem together. Let's begin by writing 4 and 36 in exponential form. 4 is 2 squared and 36 is 6 squared. Now let's recall some laws of exponents. If we have the quantity x raised to a all raised to b, we can apply the power of power rule of exponents to get x raised to a times b. We simply multiplied a times b. But since multiplication is commutative, we can also write this as b times a, and getting its converse, we can rewrite this further as x raised to b all raised to a. The reason is we notice that there is an exponent 2 here, there is an exponent 2 here, and there is a minus sign, so we know that we can turn this into a difference of 2 squares. So let's carry that out. This is what we have. We interchange the exponent inside and the exponent outside to get this expression, the same explanation for the second term. Now, since we have a difference of 2 squares here now, then we can now rewrite this applying this formula. In here, our x is 2 raised to a, our y is 6 raised to b, and so we now have this result. The difference of 2 squares, 2 raised to a and 6 raised to b, is now equal to the product of the sum and difference of these two numbers. Again, we copy equals 28 at the right side. Let's now concentrate on this equation at the right side. Notice that the base here is even, so if you raise 2 to any positive integer, then 2 raised to that number would always be an even number. And 6 is an even number raised to any positive integer, then 6 raised to that number is also an even number. And the sum of 2 even numbers is another even number. Also, the difference of 2 even numbers would always be an even number. Another thing that we observed here is a and b are positive integers, and we are adding 2 raised to that positive integer plus 6 raised to that positive integer. We know that the result of 2 raised to a plus 6 raised to b must be a positive number. And since 28 is positive, then this second factor must also be positive because positive times positive is equal to positive. We also note here that 2 raised to a plus 6 raised to b must be greater than the second factor because we have here addition and we have here subtraction. Now let's take a look at positive 28. What are the possible factors of 28? We have 1 times 28, we have 2 times 14, and we have 4 times 7. We want the factors to be both even and both positive. So clearly, 1 times 28 is not that pair of solutions because 1 is an odd number, so let's remove it. Also, 7 is not an even number, so let's remove 4 times 7. We are only left with 2 times 14. And we said that the first factor here is greater than the second factor. So it is 2 raised to a plus 6 raised to b that is equal to 14. And 2 raised to a minus 6 raised to b is equal to 2. And so we now have this result. Now, we can solve these two equations simultaneously. This is now what we have. Adding 2 raised to a plus 2 raised to a, we have 2 times 2 raised to a. 6 raised to b minus 6 raised to b is 0. 14 plus 2 is, of course, 16. And solving now for a, we divide both sides by 2 to get 8 at the right side. And 8 can be written as 2 raised to the third. And so clearly, a is equal to positive 3, which is a positive integer solution. So a now is equal to 3. Then substituting this result, a equals 3, to one of the equations we solved simultaneously a while ago, we now have 2. Instead of a, we have this 3, copy all the rest, but 2 raised to the third is 8, and 14 minus 8 is 6. So we now have 6 raised to b equals 6, and finally, b is equal to 1. So the value of b now is equal to 1, and let's check if our answer is correct. Substituting the results for a and b to the original equation, we now arrive at 64 minus 36 equals 28, which is indeed a correct equation. So our final answers are a equals 3 and b equals 1, and both are positive integer solutions to this given Diophantine equation. We are given a raised to b is equal to 343, b raised to c is equal to 10, and a raised to c is equal to 7. We would like to find the value of b raised to b. Now let's solve this problem together. Let's begin with the given a raised to b equals 343. Now this 343 can be written as 7 raised to the third. But it is given that a raised to c is equal to 7. So we can replace the 7 by a raised to c. Now let's recall the power rule of exponent. When we have the quantity x raised to m raised to n, that is equal to x raised to the product of m times n. So clearly from here, the quantity a raised to c raised to the third is exactly the same form as the left side of this power rule. And therefore, this can be simplified similar to this right form. And therefore, we now have this equation, a raised to b is equal to a raised to the product of c and 3, which is 3c. Now, since in this equation, the base a at the left side is the same as the base a at the right side, it follows that the exponent b is equal to this exponent 3c. So we arrive at this equation, b is equal to 3c. Now let's remember these values. Let us recall that what we are looking for here is the value of b raised to b. So we can begin with this identity. Any number is equal to itself. But we know that the value of b is equal to 3c. So we can replace this b by 3c to arrive at this equation. Now again, let's go back to the power rule. If we take the converse of this power rule, if we start with x raised to m times n, which is the form of b raised to 3 times c, where our m is 3 and our n is c, then we can write this b raised to 3c into a form similar to this left side of the power rule. And by commutative property of multiplication, it doesn't matter whether 3 comes first or c comes first. And so, this right side can be rewritten as the quantity b raised to c all raised to the third. And to check if this is correct, by applying the power rule, we still get b raised to 3c when this form is simplified. Now, the beauty of rewriting this equation this way is because we know the value of b raised to c. It's given to be 10. So therefore, we can replace this b raised to c by 10 to arrive now at b raised to b equals 10 to the third, where 10 is equal to b raised to c, and 10 to the third is equal to 1000, which is now the value of b raised to b. Thank you very much.